In June 1816, farmers in New England watched frost return during the growing season. Across parts of Europe, cold rain soaked fields that should have been ripening beneath the summer sun. Harvests weakened. Food prices rose. Communities struggled through weather that seemed to belong to another season. The year would become known as the year without a summer. But the cause was not in America or Europe. It was thousands of miles away, on an Indonesian island, where a mountain had exploded more than a year earlier. That mountain was Tambora, and its eruption would become one of the clearest demonstrations in recorded history that a disaster in one part of the world could alter conditions across the entire planet. Tambora rises from the Sanggar Peninsula on the northern side of Sumbawa, an island in what is now Indonesia. Today, its summit stands about 2,850 meters above sea level. Before the Great Eruption, geological reconstruction indicates that the volcano may have risen to approximately 4,000 meters. Tambora was part of the Sunda volcanic arc, a region created by the movement of tectonic plates beneath the Indonesian archipelago. For generations, communities lived and farmed around its slopes, connected to the wider maritime world of Southeast Asia. The mountain had been showing signs of activity since around 1812. But nothing in recorded human experience could fully prepare the surrounding population for what began in April 1815. Tambora entered its catastrophic phase. An enormous explosive eruption tore through the summit. Ash, pumice, volcanic gases, and superheated material were driven into the atmosphere. Pyroclastic flows, fast-moving mixtures of hot gas, ash, and rock, raced down the volcano and reached the sea around the peninsula. The eruption also generated a tsunami and destroyed settlements, farmland, and local food supplies. By the time the main eruptive sequence ended, the upper part of Tambora had collapsed inward. In its place was a caldera approximately 6 kilometers wide and more than a kilometer deep. The Smithsonian Institution's Global Volcanism Program classifies the eruption at Volcanic Explosivity Index 7. It estimates that more than 150 cubic kilometers of tephra were produced and that the disaster and its aftermath caused roughly 60,000 deaths. Other historical estimates differ, partly because records from the region were incomplete and many people died later from hunger and disease rather than from the initial explosion. Tayan's first victims were the people closest to Tambora. Heavy ashfall devastated croplands. Livestock, water sources, transportation, and local trade were disrupted. Food shortages continued after the immediate destruction had ended. This local catastrophe can easily disappear from popular versions of the story, which often move quickly from Indonesia to strange weather in Europe and North America. But Tambora was not simply a volcano that made distant countries colder. It was first a human disaster in Southeast Asia, one whose survivors faced destroyed communities long before the rest of the world understood that anything unusual had happened. Material that would change global climate was not primarily the heavy ash that fell near the volcano. The most important long-distance influence came from sulfur dioxide driven high into the atmosphere. There, chemical reactions transformed the gas into sulfate aerosols, tiny particles capable of reflecting part of the sun's incoming energy back toward space. Ordinary volcanic ash usually falls from the atmosphere relatively quickly. Sulfate aerosols can remain at high altitude much longer, spreading across enormous areas and reducing the amount of solar energy reaching Earth's surface. Because Tambora was located in the tropics, atmospheric circulation could distribute its volcanic aerosols into both hemispheres. Scientific estimates vary, but one peer-reviewed reconstruction calculated that the eruption released approximately 51 to 58 million metric tons of sulfur dioxide. Tambora had effectively placed a thin, sunlight-reflecting veil around much of the planet. Response was not identical everywhere. Some locations experienced unusual cold. Others received abnormal rainfall or faced altered seasonal patterns. Ocean circulation, geography, atmospheric conditions, and natural climate variability all influenced what individual communities experienced. A climate modeling study estimated that global average surface temperature fell by roughly 1 degree Celsius during the peak cooling in 1816, with cooling over land greater than over the oceans. The same research estimated a global reduction in precipitation, although regional results varied greatly. A difference of 1 degree may sound small. But global averages conceal intense local disruptions, and agriculture depends not only on average temperature but also on frost dates, rainfall, sunlight, and the timing of each growing season. Northeastern United States, historical records describe abnormal cold and repeated summer frosts that damaged crops. At the time, no one in New England knew that a volcano in Indonesia was influencing the atmosphere. Some observers searched for other explanations. The Reverend Jonathan Fisher of Maine, for example, recorded sunspots while trying to understand whether changes in the sun might be connected to the strange weather. His observations reveal something important: people living through the crisis could document its effects, but they lacked the global scientific network needed to identify its distant cause. The connection between Tambora and 1816 would be established only through later historical and scientific investigation. LSO endured severe disruption. The summer of 1816 was unusually cold and wet across significant parts of the continent. Poor harvests contributed to food shortages, rising prices, malnutrition, unrest, and disease in vulnerable communities. But climate did not act alone. The Napoleonic Wars had ended only recently, leaving economic disruption and social instability. Access to food depended on income, local government decisions, transportation, markets, and existing inequality. The same weather could therefore create inconvenience for one household and disaster for another. Tambora did not automatically produce famine everywhere. It intensified pressure on societies that already had limited ability to absorb another shock. Phrase, Tambora caused the year without a summer requires some qualification. Evidence from polar ice cores indicates that another major tropical eruption occurred around 1809. The volcano responsible has not been identified with certainty, but its sulfur had already contributed to a colder period before Tambora erupted. The early 19th century also occurred near the end of the Little Ice Age, during a period of relatively low solar activity commonly called the Dalton minimum. Tambora was the major immediate volcanic force behind the extraordinary conditions of 1816, but it acted within a climate system already affected by earlier volcanic activity and natural variability. Modern research therefore does not describe the decade as the product of one simple cause. Tambora was the most dramatic event in a larger chain of influences. T.S. reconstructed this story using evidence that the people of 1816 could never have assembled. Ice cores from Greenland and Antarctica preserved layers containing volcanic sulfate. Tree rings recorded years of restricted growth and unusual environmental stress. Historical weather journals documented frost, rain, temperature, and failed harvests. Geological surveys measured the immense caldera and mapped the deposits left across Sumbawa. Climate models then tested how a tropical eruption of Tambora's size could alter temperature, rainfall, and atmospheric circulation. No single form of evidence tells the entire story. Together, they connect an explosion in Indonesia to climatic disruption across distant continents. Also changed how scientists understand volcanic danger. A volcano does not need to cover the world in visible ash to affect global climate. The crucial factor is whether a major eruption sends enough sulfur into the stratosphere, where sulfate aerosols can remain and reflect sunlight. Later eruptions, especially Mount Pinatubo in 1991, allowed scientists to observe this process using satellites and modern instruments. Those observations helped confirm mechanisms that researchers had reconstructed from Tambora's geological and historical evidence. Tambora remains an important case study because it shows how atmospheric change can become a food security crisis. A harvest may fail far from the eruption. Prices may rise in cities that never see the volcano. Communities with fewer resources may suffer most severely, even when the average global temperature change appears modest. 2 centuries later, Tambora's caldera still dominates the summit of the mountain. It is a physical absence, the empty space left when the volcano destroyed and collapsed part of itself. But Tambora's larger legacy is found far beyond Indonesia. It survives in damaged tree rings, sulfate preserved in polar ice, records of summer frost in New England, accounts of failed European harvests, and evidence of the communities on Sumbawa that faced the eruption first and suffered most directly. The summer of 1816 was not literally erased. Sunlight still reached the ground, crops still grew in some regions, and weather varied from place to place. Yet for millions of people, the season did not behave as summer was supposed to behave. And behind that global disturbance stood a volcano many of them had never heard of, a mountain in Indonesia powerful enough to change the color of the sky, disrupt harvests across continents, and make the world feel colder. Tambora did not merely erupt. It revealed that Earth's atmosphere connects every nation beneath it.